Welcome to the chapter Residence Time Distribution. Now that we have learned which basic flow models exist, I also want to show you why we need them. A fundamental concept for continuous flow processes is the residence time distribution. But what is the residence time distribution? This concept was first described in 1953 by P. Danckwerts. It helps to solve a question that is not so easy to answer, which is if the material enters the process at a given point in time, when will it come out again and in which condition? By condition I mean here the level of mixing with material which entered the process at a different time. We define residence time distribution, or RTD, as we call it also, the concentration of a substance at the outlet in relation to the concentration entering on a timed basis. Please do not confuse this with a chemical reaction taking place. Of course, chemical reactions can also take place in flow, but this is an even more complex case. In the case of a chemical reaction, the concentration changes because the chemical reaction and because of the mixing with the material which entered at a different time. So let's for now think about the simple process of mixing of two components without any chemical reaction taking place. If you think about the continuous stirred tank, substances A and B enter the reactor at the same time, and at the outlet you have an ideal mixture of both substances. You now might think, well, the concentration does not change at the outlet, and yes, this is correct. The ratio of A to B does not change. But now we look at the system in more detail. We examine the individual particle or molecule. The molecules enter the system in bulk, specific molecules next to each other. Once they enter the reactor, they are mixed with the other molecules that were already in the tank. So one particle or molecule of the bulk might exit immediately, one might take some extra turns, and another even more. This means that if we think about the concentration of the specific bulk at the inlet, the concentration at the outlet is different. The time it takes the individual molecules to leave the system is what gives us the time-based distribution that we call residence time distribution. Why is this so important for pharmaceutical manufacturing processes? Why measure and investigate the RTD? Let's look at an example process to understand this better. Here I show you a simplified process setup. We have 3 feeders that feed a continuous flow of material into a blender. Then the material moves into a granulator and finally into the tablet press. This process involves some more steps in between, but this is a simplification and is sufficient for us now. The material from the feeder enters the blender at time 0, and what you see here in pink is the concentration of that same material exiting the blender. You see in the graph that there is a delay until that material has left the blender. If we also look at the bulk of material entering the granulator, you see that the material also leaves the granulator with some delay. The same happens inside the tablet press if you look at the purple line. And if we look now at the material concentration in the tablets, this is quite different. It's the yellow curve. Again, we are talking about the concentration of individual particles and molecules of a tracer substance that we added, not at the concentration of the excipients or API. So if we add all that delay and mixing that occurs in the blender, the granulator and the tablet press, we end up with a yellow curve. Considering that these particles once entered the process in one bulk or one group all together at the same time, we have quite a spread of that same material. A little more than 1000 seconds in this case, so about 16 minutes. Going back to our initial question, why measure RTD? If you have a batch of excipient in the feeder and you turn it on and let it through the plant, this distribution will help you to determine how much of batch A is in the next batch B. And you can set boundaries for acceptable levels of batch A in batch B and use this for batch definition. I already mentioned that batch definition works a little different in continuous manufacturing, and we'll hear more about that later. Another problem that can be tackled with knowledge of residence time distribution is the treatment of material that is out of spec. If you realize that a very small fraction of your material, let's say in the granulator, is out of spec because it's too wet or too large, you can discard it before you press it into tablets. The knowledge of residence time distribution will tell you exactly how much of the material you have to discard, and you only need to discard this small fraction. This is a very significant advantage of continuous manufacturing. Now that we have established how to define the residence time distribution, or RTD, and why it is important, we want to learn how we can quantify and describe it. To measure RTD, several options are possible. One straightforward approach is to add a tracer element to the system and measure the impulse response, which means the concentration of the tracer at the outlet on a time basis. This function is the E of t function. So, what is E of t? E of t is the probability that a specific portion of the material that entered the system at t equals 0 leaves the system at the time point t. It is sometimes also called the exit age distribution or differential distribution function. This also indicates that we measure the time the material was in the system until it left and what is the distribution of that time. E of t can also be mathematically quantified. Let me write that down for you. So E of t is calculated by the division of C of t with the integral of C of t dt from 0 to infinity. C of t is the function of the concentration at the outlet in relation to time. The integral from E of t dt from 0 to infinity equals 1. This is a logical consequence of what E of t is. E of t is the impulse response to a pulse entering the system. After an infinite time, all of the material has left the reactor. So the sum of all tracer that left the reactor is the same as the material that entered it. When we look at the material that is staying in the system, we can quantify that by using the washout function. For the washout function, we assume that the concentration at the inlet and the concentration at the outlet is the same. This means that we had the tracer running constantly through the system until the concentration stabilized, which results in C being equal to C out, being equal to C0. Then we suddenly stop the tracer at the inlet, so C in is 0. What we measure is the time that it takes for the concentration at the outlet to drop to 0 as well. As you can see, it is defined by the concentration at the outlet at the time t divided with the concentration C0, which is the concentration at the outlet at the start. W of t is 1 at the start and decreases to 0 over time. Now we know the distribution over time, but it's also good to know the mean residence time. So the mean time a molecule or particle stays in the system. The mean residence time in the system has the symbol tau, and it is defined as the division of capital V, the volume of the reactor or the mass of the reactor, by V dot, the volume flow through the reactor. The dot indicates that we are talking about a flow rate. So while the unit for the volume of the reactor is liters, it can also be mass-based, so kilograms. The flow rate through the reactor is liters per hour or kilograms per minute, etc. Therefore, the resulting unit for tau is time, seconds, minutes, hours. Tau is calculated by the holdup divided with the throughput. Keep that in mind. You don't need the time-based distribution to calculate the mean residence time. You only need to know the volume and the flow rate. But of course, you can calculate it also from the exit age distribution or the washout function. F of t is also an important parameter to define. It is the cumulative distribution function. If I write it down, you see that f of t is calculated by forming the integral from E of t dt from 0 to t. We already learned that the integral from E of t dt from 0 to infinity is 1. So f of t is a function with the maximum at 1. f of t depends on the time it takes various portions of the material to flow through the equipment. Therefore, it is the distribution of residence times. It is also called the cumulative distribution function. Also, f of t is the response function if you carry out a step exchange experiment, so if you have a complete permanent change of material at the inlet. Don't worry, we will talk about that in more detail later. This was a very intense session. Therefore, let me quickly summarize for you what we have learned. Residence time distribution is the concentration of a substance at the outlet in relation to the concentration entering on a time basis. Tau is the mean residence time and can be calculated without knowing the time-based distribution. E of t is the probability distribution or exit age distribution, and its integral to infinity is 1. F of t is the cumulative distribution function, and its maximum is 1. With that, I'd like to thank you for your attention and make sure to check out the quiz for this session.